by step, starting from brute force and finally reaching an optimal solution. This problem is very useful for understanding sliding window techniques, minimum queries, and time complexity optimization, which we commonly asked in technical interviews and competitive programming. Now, if we go with the problem statement, let us first understand this problem clearly. We are given two integers n and k, where n is the total number of elements in a sequence and k is the window size. The sequence is not given directly, instead it is generated using four values x, a, b and c. The first element is already given as x and every next element is calculated using the formula. After generating the full array size of n, our task is take all sliding windows of size k, find the minimum element in each window, compute the XOR of all these three minimum values. Next, constraints is the main part where we need to optimize the solution. Here, number of test cases can go up to 10 and n and k can be as large as 10 power 7. Values of x, a, b and c can go up to 10 power 9. A simple nested loop here will be too slow because the values are very large. This is the main reason why we explore multiple approaches in this presentation. And if we go with the input-output format, for each test case, first line contains n and k and second line contains x, a, b and c. These are sequence generation parameters. And in output, for each test case, we print a single integral value representing the XOR sum of all window minimums. Next, the approaches will be continued by my teammate.
Here we have approach 1, which is brute force. Here we have ideology as we generate all the slide windows and find the minimum of each window, and by finding each minimum of window we should XOR all the minimums, so we get the XOR of all the slides minimums. Next, let's assume a test case, sample test case where n equal to 8 and k equal to 5, and then generated sequence of f is 3, 0, 1, 8, 2, 4, 7 and 6. Our goal is to find the XOR of minimums of all the window size of k, where all the possible window size k equal to 5 are here we have first window of 3, 0, 1, 8 and 2. Here minimum is 0. In this way we generate all the minimums of each window. It will take a time complexity of order of n k in for generating minimum from each window. Here we have 0, 1, 2 or minimum, or then we generate XOR as a result. Next, here we have approach table as our approach is brute force. It will take time complexity of order of n into k, where n is the number of elements in the given array and k is the size of window, where the space complexity is order of 1. We move to second approach, which is reusing previous window. Our ideology is to reuse the previous window minimum. We recompute only if the outgoing element was minimum. In best case, we will get a complexity in order of n, and in worst case, will get order of n into k, where k is the size of window, where n is the number of elements in the generated sequence. If the outgoing element is not minimum, we can reuse the minimum of previous window. This is the in first window we have 0 3 0 1 8 2, and then we got minimum of 0. And whereas if moving the slide, our outgoing value is 3. So we can reuse the 0 minimum, which is previous minimum. In this way, we generate to next slide as 1 8 2 4 7, and we have minimum 1, where outgoing element is 1. We should recompute the minimum value, as our next slide is 8. Next slide contains elements 8 2 4 7 and 6, and we have minimum 2. In this way, we can reuse the previous minimum values if the outgoing element is minimum. If the outgoing element is minimum, we should recompute the minimum value, as our windows minimums are 0 0 1 2. The XOR result of 0 0 1 2 is 3. In best case, it will take a complexity of order of n, where in worst case, it will time complexity will be of order of n into k. Next, we go for approach table, where our approach is of reuse previous minimum. Our then our time complexity would be using sliding window. We use tree map in sliding window, which tree map stores the key value based values in the tree map, that which makes us to easy for pick off minimum from window, where the operations in tree map will be having a time complexity of order of log n, where the n is the total number of elements in the generated sequence, where total complexity is of order of n into log k, where log k is the operations complexity in the tree map. Next slide. Let us assume the same sample test case where n equal to 8, k equal to 5, and then generated sequence f is 3 0 1 8 2 4 7 and 6. Here also our goal is to find the XOR of minimums of all windows of size k, where possible windows in of tree map are 0 1, where 1 is the frequency of 0 in the window 1, where 1 is the second key and its frequency is 1, where we store values in the key where values has frequency, so that we can easily pick the minimum, where the tree map stores in a sorted order, where the first element is the minimum value, so that it makes us to pick easy of minimum. And our possible window minimums are 0 0 1 and 2, and final XOR result is 3. An approach table is where we firstly come from source, which takes order of n into k, time complexity and space complexity is of 1, where reuse previous sliding window, which take worst case of same as brute force, and when it comes to best case, it will take in order of n, where the space complexity is same as brute force, order of 1, where our approach 3 will having sliding window. Our approach 3 sliding window tree map will have a time complexity of order of n into log k, where n is the number of frequency number of
Divide array into blocks of size k. First we pre-compute prefix minimums that we will be calling as left, and next we pre-compute the suffix minimums that we will be calling as right. So now the main important point is, first we need to divide the complete array into blocks of size k. Each block is processed independently here. Now let us consider an example. Here this array is divided into two blocks, 30182 as one block and 476 as another block. Now we are trying to building left for block 1. First index will be starting from 0, so it is the start of the block. We already said that left of I, if it is the start of the block, then left of I becomes array of I. So the left of 0 becomes 3. Next, when we come to I equals to 1, it is not the starting of the block. So it compares minimum of left of I minus 1 comma array of I. So when we compare left of 1, when we compare left of now currently the index is 1, so we compare left of I minus 1, that is 0. Left of 0 comma current element is also 0, so the minimum of 0 comma 0 will be 0. Next, when I equals to 2, we compare with left of 1 comma current element, so the minimum between 0 comma 1 will be 0, and next I becomes 3. So now we compare left of 2, that is 0, with current element, that is 8. The minimum of 0 and 8 will be 0. In the same way, we compare for the last index also. So for the block 1, we have created the left array that is followed as 3000. And for the block 2 also, we compare in the same way. We start from I equals to 5. So this is considered as the starting of the block. So now it is starting of the block, so left of 5 becomes current element. Then next we compare I equal to 6. If this is, now we see that this is not the starting of the block, so we compare minimum of I minus 1 comma current element, so it becomes array of I, minimum of array of 5 comma current element, that is the minimum between 4 and 7 is 4. So we return 4 here. It will compare in the same value for the next element also. Here we can ensure that minimum grows from left to right. That means it it uh, it compulsorily decreases from left to right, but it does not increase. But when we come with prefix suffix array, yes, now we understood the prefix array, right? Let's move to suffix minimum array, which is also called as right array. Both prefix and suffix arrays work together, help us finding the sliding window minimum efficiently. So what does suffix minimum mean? The minimum value from current index to end of the block. This is why this array is named as right, because we process the array from right to left inside each block. That means we process from this end to the left. So here also we will divide the total array into two blocks. Suffix minimum resets at the end of the each block. So at index I, right of I tells us what is the smallest value from here till block ends. So here also we will be having two rules for constructing right array. If the index is pointing to the end of the block, then right of the index becomes the array current element. If it is not the end of the block, we compare current element with the next suffix minimum. Here, why we set I, if I is the end of the block, right of I equals to array of I means There are no elements after this inside the block. So the minimum from this position to the end will be itself, the element itself. And yeah, let's understand with the full example. We will consider the same example again. Here it is divided into two blocks as I have already said. Now we process it to right to left. No, first the index will be pointing to 4. The it is the end of the block. So the right of the 4 becomes 2 only. Then if index equals to 3, then we compare, as I have already said, if it is not in the end of the block, we compare minimum of right I plus 1, that means next element, and array of I. So here we compare with a right of I plus 1, that means right of 3 and current element, that will be 1. So when we compare it with the minimum will be as 1. So now again we compare it with right of 2, that means 1, and the current element 0. So the minimum will be 0. Then again we compare now the index will be 0. So for the right of 0 we compare it with minimum of right of 1, that is right of I plus 1, and current element, that is 3. So the right becomes 0. Here minimum grows from right to left inside A and B. Then if we move to the next block, I equals to V point directly to the end of the block. Here the index is 7. So the right of 7 will also be current element, that is 6. Then if we go to right of 6, we compare with right of 7 and current element. So here it can be said as 6. We compare it minimum of 6 and 7. The minimum is 6. So we return 6 here. And then for the right of 5, we compare it with right of I plus 1, that is 6, and current element, that is 4. So the minimum is 4. So here comes the main formula. Now we come to the most important and final idea of this entire solution, the window minimum formula. Up to now we have divided array into blocks, build the prefix minimum array, that is left, and suffix minimum array right. For a window starting at index I, the window minimum can be said as minimum of right of I, left of I plus k minus 1. At first glance, this formula may look simple but is extremely powerful. Let us understand why this formula works. A sliding window of size k starting at index I spans from I to I plus k minus 1. So roll of right, this value right of I represents the minimum value from index I to the end of the current block. This means right of I covers from left portion of the sliding window, especially useful when the window crosses a block boundary. Now we try to understand the role of left of I plus k minus 1. This represents the minimum value starting of the block to the index up to I plus k minus 1. That means it covers the right portion of the sliding window. It captures all elements towards the window's head. Why taking minimum of both works? Together, this formula, in this formula, right of I covers window from left to left side. And so yeah, in this formula, right of I covers window from left side and left of I plus k minus 1 covers the window from right side. Every element of the sliding window is included at least here. And then when we go to the next example, here as we have already seen, the array is 30182 476. The window size is already given as 5, and we have already computed the prefix array, that is 3000444, And suffix array also 0, 0, 1, 2, 2, 4, 6. Now, here using the formula, minimum of right of I comma left of I plus k minus 1. The window ranges from 0 to 4. So in the right of 0 element, we are having 0. The left of I plus k minus 1, that means left of 4. In the left of 4, we are also having 0. So minimum of 0 comma 0 will be always 0. Next, minimum of right of 1. So the index is increasing 1 by 1 here. Right of 1 and left of 5. So if we see the array, right of 1 is 0 and left of 3 will be 0. Left of 5 will be 4. So the minimum of 0 comma 4 will be also 0. In the same way, we calculate for this window range, in this window ranges up to the n length. So we can find all, we can get the all window minimums. And the question for us is to find the XOR of all window minimums. If we XOR all these window minimums, we can achieve the answer. Where it comes to 0 XOR 0, it is 0. 0 XOR 1, it will be 1. 1 XOR 2, if we compute, it will be 3. This is the main approach. So now when we come to the approaches table, first we started with brute force, which remains time complexity as big O of n into k, and the space is not used. So it is constant. Now when we, for coming from the, for the next approach, we used previous window minimums. If it is minimum, then if the outgoing element is minimum, we calculated the minimum, or else we did not calculate. So in the best case, it will be big O of n, which is optimal, but in the worst case, it will be big O of n into k, which can lead to TLE, and the space is also not used. So we come for better approach. Then we use the sliding window using tree map. Tree map stores in sorted manner. So for sorting, we are having the time complexity big O of n into log k. Otherwise, it is also can be achieved. It is also can be said as optimal approach. And also space is also used for creating a tree map. So it can lead to TLE sometimes. So now for the in the prefix and suffix, we we traverse the total array only once. So the time complexity becomes big O of n, and the space also becomes big O of n. As we store the elements for left and right, we traverse again all. So this is what we achieved as optimal solution. First it is n into k, and last it is n. This is what optimal approach mean. So here, when we come to a conclusion, we started from a brute force, optimized it step by step, achieved an optimal solution, big O of n with time complexity. So this is what we are expected to tell. Thank you so much.
Thank you.